Okay, I'm going to pretty much start where we left off in class today, and you may want to pause this from time to time to catch up because I'm going to try to make it pretty quick for you guys. So, what are the conditions for conducting a two-sample z-test for a difference in proportions, and how are these conditions different from the conditions for a two-sample z-test, or z-interval, I'm sorry, for a difference in proportions? So, there was a typo right there that should say 2. So basically, we need to talk about the conditions. The data must come from random samples, and we'd have two samples chosen from two independent or separate populations. Or the data must come from a randomized experiment where you have random assignment to treatment groups and you have data to compare from the two different treatment groups. Next is independence. Independence gets a little bit more complicated when you have a two-sample scenario. So first, the observations within the sample or groups must be independent of each other. And this is going to be the 10% condition that you guys are familiar with. And the samples or groups must be independent between each other. So this means that you must think about independence within a sample or group, and then also between samples and groups, depending whether you have treatment groups or you have samples. So the independent condition must be met. Normality is met for a proportion the same way it has been in the past, except now you have two samples. So you need to make sure you have 10 successes and 10 failures from both samples. So basically you're going to use the formula n sub 1, p sub 1, n sub 1, 1 minus p sub 1, but you have to do the same thing for the second sample as well. So make sure to have 10 successes and 10 failures. So the conditions are the same for an interval and for a significance test, except for one thing. The standard error formula is a little different, so let's go through that. So the reason that the test has to use a different p-value is because we are assuming that the null is true. So if the null is true and that p sub 1 is equal to p sub 2, I can't use different p-hats in the standard error computation. So I have to average the p-hats. We called that combining or pooling in class. And remember that it's simply going to be that p-hat combined is going to be x sub 1 plus x sub 2 over n sub 1 plus n sub 2. So it's your number of total successes over the number in both samples. So that's the only thing that changes between the two different formulas. So the interval uses p at sub 1 and p at sub 2. Whereas the test of significance has to assume the null is true, and that's when you know to shift and use a different p, and it's going to be the p hat combined. So let's do our first example here. So our teenagers going deaf in a study of 3,000 randomly selected teenagers in 1988 to 1994, 15% showed some hearing loss. In a similar study of 1,800 teens in 2005 to 2006, 19.5 showed some hearing loss. So yes, it appears there's a difference, but is it significant? And especially, can you actually infer that back to the population and say that yes, the population has had an increase in hearing loss? So let's continue on. So do these data give convincing evidence that the proportion of all teens with hearing loss has increased? So we're going to do a state plan do conclude here. So state, we will test the null claim that says the two proportions are the same, that p sub 1 minus p sub 2 is equal to 0. And you guys remember that I told you in class you could also say p sub 1 equals p sub 2. That's saying the same thing. Just wanted to point that out. Okay? Versus the alternative, which says that p sub 1 minus p sub 2 is greater than 0. So you could also write this alternatively as p sub 1 is greater than p sub 2. Now, we have to be careful that what we're claiming matches what we're suspecting. In other words, here we're saying the proportion of hearing loss should be larger in p sub 1. That means that we need to use the later population for p sub 1, so we need to identify that. We're going to use an alpha 0.05 significance level, and p sub 1 will be the proportion of all teenagers with hearing loss in the later time period, where p sub 2 will be the hearing loss or proportion in the earlier time period. We are expecting to get positive values, so think it through. P sub 1 would have to be bigger. Now, I'm not talking about p hat sub 1. I'm talking about the claim made that hearing loss has increased. So we're going to actually do a 2-sample z-test for a difference in p sub 1 minus p sub 2, only if the conditions are satisfied. So first, the random condition says the data came from 2 separate random samples, and normality, we have 4 different things to check, and we already know that p hat sub 1 is going to be 0.15. So you could and should actually show for each of these. So n sub 1, which was our second sample, we need to make sure we get the right thing. N sub 1 is going to be for 1,800 students, 1,800, and of those, well, 19%, 0.195 showed hearing loss, and of course that's going to give us, it should give us 351. So 351 is the number of successes, the number of students saying that they have had hearing loss in the later time period, but you want to compute all those. So moving on, independence. The samples were taken independently, and there were more than 10 times 1,800 or 18,000 teens in the later time period, and 10 times 3,000 or 30,000 teens in the earlier time period. So our conditions have been met, so we're going to move on to our do part. So the first thing you want to do is you want to make sure you understand what is your combined p hat. So you take both, you take both of your values for your successes. So 351 actually came from the later time period, and 450 came from the earlier, divided by the sample size. So my average success, or the average proportion of students with hearing loss, is 0.167. So we're going to use that for our actual standard error formula. All right, so let's use our formula. Let's set it up. So z is going to be p sub 1, or p hat sub 1, which is 0.195 minus 0.15. And these are just given in the problem. And that will be subtracting 0, because the claim is that there is no difference. So this is always the hypothesized value, all over the square root, and I have to use my combined p hat here. So 0.167, 1 minus 0.167, all over n sub 1, and n sub 1 is 1,800, plus the same numerator again, and this will be over 3,000. So when I compute all that, I get 4.05. So I'm looking for the probability that any randomly selected z will be greater than 4.05. So that will be normal, CDF, and I would use 4.05 to infinity, 0, 1. And it's because I already have the z-score, so the data has been standardized, and I'm going to get approximately 0. So very, very unlikely that we would observe those differences just by chance. So that's what that's saying there. Okay, let's conclude. So since the p-value is less than alpha, and you want to give it some numbers here, 0 is less than 0.05, obviously, we are going to reject the null claim. We have convincing evidence that the proportion of all teens with hearing loss has actually increased from 1988, 94, to 2005, 2006. All right, so between the two studies, Apple introduced the iPod. If the results of the test are statistically significant, can we blame iPods for the increased hearing loss in teens? So the answer is going to be no, we cannot. Because this is just something we're observing. There was no control, there was no random assignment. So it wasn't an experiment. So since we did not do an experiment where we randomly assigned some teens, to listen to iPods and other teens to avoid listening to iPods, we cannot conclude that iPods are the cause. It is possible that teens who listen to iPods also like to listen to music in their cars, and perhaps the car stereos are causing the hearing loss. In other words,